all morphogenesis is trying to answer the question of what the hell am I? And what is the most sort of efficacious a coherent story that I can tell in anatomical space. First, the definition. So xenobots are self-assembled from frog embryo epithelial cells. Neurobots, which were first created by Hale Forowat in my lab, who's now at Harvard, she introduced neurons into them. So they're basically xenobots with a core of neural cells inside. So they have a nervous system. So, the reason I wanted to do that work was I'm curious, like if you look at a standard animal with a standard nervous system and you say, why does it have that kind of nervous system? Usually you say, well, because evolutionarily, here's the environments it had to deal with. Here are the ancestors that it had. And therefore, the nervous system has been shaped by selection pressure to have specific properties and whatever. Well, there have never been any xenobots. There have never been any neurobots. There's never been selection pressure to be a great neurobot. So my question was, what the hell does a nervous system look like in a creature that's never existed before? I mean, obviously frogs have existed, but xenobots are not frogs. They don't look like frogs and have the same body plan. So what would that look like? So that's what I was interested in. And we've done some behavioral analysis. We need to do tons more. I mean, so there are obviously some differences. But the thing about knowing what to predict is I don't necessarily know what to predict from anesthesia, even in xenobots in the first place. Like one of the things that we're doing is, and this is some work with Anil Seth's group and some other folks, to look at metrics that people are using to judge, conscious awareness, wakefulness, sleep, coma, nobody home, all of the different options that use different kinds of metrics. There's causal emergence and whatever. There's all these tools. So just to understand first, can we even say what is it that these anesthetics are going to do in a xenobot? Is it going to stop moving? Is it going to not be able to solve certain problems that it could solve before, which we're still characterizing all the things that it can do? It's not super clear to me. What the one prediction that I will give is that I think whether with neurons or without neurons, I think we're going to find important differences. And I think that, yes, no doubt the neurons are going to add some cool like bells and whistles on it. But the fundamental phenomenon, I think we're already going to see with epithelial cells. I don't think it's going to be unique to neurons.
That would be great. But I mean, like things like propofol, which is a common anesthetic, acts on GABA receptors in the neurons. So what's the equivalent of that in your xenobot?
I don't remember it specifically if xenobots have GABA, but GABA's like those receptors are
neurobots too.
Yeah, they're present.
Let's do that experiment. Yeah,
it's goblet cells, right? Goblet cells have, I believe, goblet cells have GABA receptors.
I think. All right. I'm embarrassed. I don't remember exactly. Because I know we did. Well, like we've did the transcriptomes. We know exactly what's there. Let's put it this way. In general, lots of machinery that you find that's neural machinery, like all the serotonergic stuff. The glycine receptors, GABA, like that stuff is present in all kinds of cells. So it may well be there.
Let's anesthetize. Let's start with neurobots. Let's anesthetize them. I mean, so this, by the way, is working in anesthesia. I'm doing with Emory Brown, who's not only a professor at MIT like me, he's a practicing anesthesiologist. So
yeah.
He knows.
I think you know what? I think I emailed him for a dumb question. Like and maybe you guys have an answer to this. So I'll follow up. But a lot of the anesthetics that we try to use are not water soluble, and right. And I don't know if that's a standard thing or not, but because all of these biobots, they function underwater, basically.
Oh, that's a problem, yeah.
Right. So either we're using it or we need to get it into the water somehow. So maybe I'll pick your brain afterwards about how to do it.
But your neurobots, so they're showing these emergent like electric field dynamics, oscillatory dynamics. What's the frequency profile, right? Is it like the human brain or animal brain where it's like anywhere from 1 hertz to 100 hertz or more?
I'll send you. I'll get you a full profile and send it to you. I don't remember sitting here today. I don't remember but there are lots of we've done some calcium signaling imaging, and I bet I bet we have the kinds of things you're looking for. But let me send. We'll see.
If they're like the primate brain, a human brain, then we should see these profiles basically shift down to a lower frequency. Let's start there. Let's see if that happens. And also, it isn't just simple, signal lower frequency. There's this whole cascade of events that happens in the primary brain. First, this mid-level frequency of alpha goes up in your frontal cortex, and then that's at the start of induction. Then it cascades down so there's a whole cascade of oscillatory events. And if we could see, first of all, whether the state change is the same as in the neurobots, then whether the cascade is the same, or which elements are there, which ones aren't. That would be wicked cool.
Yeah, we should look, and it's also possible that the whole thing might, because in general, non-neural cellular bioelectricity functions several orders of magnitude slower. Like a lot of this stuff is the same, but it's just much slower. So what you might see is that the whole thing is slow, but then it gets even slower, right?
Yeah.
We might, it might be a relative.
Well, these frequencies are not magic. They're not a certain band is good for something. Just like saying a spike always does one thing or another. But even the exact frequencies don't really matter. Like human brains, like animal brains, they tend to be higher frequencies because the brains are smaller, so the recurrent connections are on a shorter scale. What's really important is the relationship between the waves. So it's more like the different brains can play the same song in different keys, basically. It's the harmonic relationship between the waves that are going to be important. You see this kind of nested cross-frequency coupling where octave effects and stuff like that. That's music is sound waves, and electric waves follow the same principle. So what's important is the relationship between the waves, not exactly what their frequency or what the exact frequency is.
How do you explain, or do you have any explanation for the visual expression genes in this neurobot? So we keep seeing this strange gene expression in these novel little creatures, as Earl said, and now I will use that phrase forever now to describe any of these things as little creatures. We saw hearing gene expression in xenobots, right? And now we're seeing visual gene expression in neurobots. And to me, this is so funny because it's almost like you have this novel accumulation of cells being dropped into an environment, and it's like it's reaching for a sensory apparatus. It's like, right, what the hell do we do, guys? Completely new environment. How can we reach for something to help us navigate this environment a little better? I'm probably extrapolating a lot there, but that's kind of seems like what's happening to me. Do you have any explanation for this?
So there's a couple of interesting things. So just to say what the basic observation is, we were interested to know what is the transcriptome of beings that have never been here before, right? So we know the standard transcriptomes have an evolutionary backstory that tells you why certain genes are up or down. At least we think they have that backstory. We assume they have that backstory. And so in these things, we just ask the question: okay, so what new genes do xenobots and anthrobots express that their parent tissues did not express? Okay, you can't do the reverse because they're obviously missing a ton of genes because they don't have endoderm, they don't have mesoderm. They're missing a bunch of, so you can't do that. But you can ask what extra gene, like what additional things do they express? So xenobots, several hundred new genes, anthrobots about 9,000, so like half the genome. And the thing is, it's you said they're in a new environment. In a certain sense, they are, but just to be clear, because a lot of people say, well, if you put things in a weird enough environment, of course they'll turn on different genes. The environment for the xenobots is basically the exact same environment the embryo was in. They're not in some crazy new set of parameters. They're in weak salt water, just like the frog embryo was. The one thing that's missing, however, are the other cells. So normally what happens is that these epithelial cells are basically bullied by all the other cells that give them a very boring life, this like outer covering of a frog embryo that's just going to keep out the bacteria. And so those are gone. So it's like engineering by subtraction. You've removed those influences, and now the tissue gets to do whatever it natively wants to do. Well, this is what it wants to do. So why are they expressing these hearing genes? So they express a whole cluster of genes related to sound perception. And we saw that. We said, well, let's stick a speaker under the dish and see if they can really, sense vibration. And sure enough, unlike embryos, xenobots, when you give them, and this is just sine wave, like a simple sine wave. We haven't done, Bach and whatever. You give them a simple sine wave, and they absolutely react differently when the sound is on. Why are they doing it? I don't know, but I kind of go with what you just said, Evan, which is that I think all morphogenesis, even normal standard embryonic all morphogenesis is trying to answer the question of what the hell am I? What is the most sort of efficacious coherent story that I can tell in anatomical space? And typically that ends up, dogs have puppies and cats have kittens because usually they answer things the same way. But what evolution made in those cases are problem solving systems that when they are in a different configuration will solve the problem in a different way. And if they have access, and I can give you other examples of complex systems using different molecular affordances to solve problems when situations get really weird. I think they're trying to, they're trying to have a more coherent life in their environment, and this is now what we're studying with, very vigorously, is to find out what exactly that plasticity is.
That what life is? Local reverses of entropy, using as little energy as possible. I mean, life kind of wants to be organized, right?
I think that's true. I don't know if I'm a little skeptical. I mean, I know it has to be tried, and there's been good work on it. I'm a little skeptical that that's the kind of that those kind of entropic explanations are going to be the whole story, or like even the best perspective. But obviously, it's a useful.
It's not really an explanation. It's kind of just more of a philosophy. But
yeah. It's a question of
how it happens is the whole story.
Well, it's a question of drive, right? What is the fundamental, you can ask people, like, what do you see as the fundamental drive of biology? And some people will say it's entropy, reduction. And some people will say it's propagation of information, right?
Sure.
The reproduction. I'm skeptical about either of those I'm not sure that's going to be enough, but those are the kinds of questions we have to ask.
Really cool. The Giant Shoulder mission is to explore radical ideas in biology, neuroscience, and consciousness, and elevate those stories to the highest possible level while keeping them accessible to everyone. If this interests you and you want to support independent science, then please consider subscribing to the Clips channel